Good morning, students. The next new topic I am taking is kinetic theory. It is actually mentioned as a kinetic theory of gases, but in this we are going to discuss some points related to the liquids and solids also. Kinetic, kinematics, kinetic, dynamic is interrelated. It is related to the force acting on the particles. So in this kinetic theory, we discuss a macroscopic relationship for the gases, interlinking with the microscopic properties of the gases like volume, pressure, how the pressure exerted on when the gas is moving are taken in the containers. Or gas moving means what? Wind exerting the pressures on the walls of the containers. Gases are of two types basically we take. One is ideal gas, another one is real gas. Ideal gas is only imaginary gas. Real gas, what you see in the daily life, are all real gases like hydrogen, nitrogen, helium, carbon dioxide. These are all what you see in the daily life, and oxygen. They are all real gases. Ideal gas is only imaginary. We take only on the paper. Theoretically, assumption we take first ideal gases and we implement for the real gases. What is the difference between these two? Is ideal gas is a particle's size. Ideal gas particle size very small compared to the container size. We take the gas in a box that called as a containers. And take the gas in the boxes, the gas particles move randomly depending on the temperature. They move, they don't stand at one place, they keep on moving randomly in all directions. They collide with each other, collide with the walls of this container. Whenever the collide, force exerted, force by area is equal to pressure. Pressure is acting on the walls, and that is called as the gas pressures. But compared to the size of this container, the gas size, particle size is very small. We have to take very negligible size. That means if you take all the gas particles together to one side, that volume occupied this gas molecules is very negligible compared to the volume of the size of this container. The particle size is very small compared to the container size. But a practical case, if you check up real gases, if you check up, they have the bigger sizes comparatively, and we cannot neglect the size of the gases compared to the size of the container. That means in case if you take all the gas particles of the real gas oxygen in the box and you push it to the one end, they occupy some space. If you compress also, they will occupy some space. So the real gases volume size cannot be neglected compared to the size of the containers. And there is no force of attraction. For ideal gases, there is no force of attraction between the molecules or atoms. That means if the molecules are there, there is no force of attraction between these two or repulsions. They have the kinetic energy motion only, but not attraction. If there is an attraction force, there will be a potential energy. But for no molecular force of attraction means potential energy is zero. But a molecular force of attraction, molecules have force of attraction, so potential energy is not equal to zero for the case of real gases. These are real gases. Next is the time interval between the collisions. In the case of these air molecules or gas particles, they are colliding with each other, hitting with each other and colliding with the walls of the containers. The particles, when they are hitting each other, the time spent to collide with each other and time spending while colliding the walls, hit and then go back, hit and get separated. During the time interval for this hitting time is very small compared to the time taken to hit with the walls or with other particles. The gas particles will take more time to reach other particles because the distance of the particles is very large in the containers. Gas particles maintain more distance with each other. So the time taken to collide is more than the time of collision or time with the walls or with each other. That point is not of much importance for us, but just have an idea of it. But not in the case of the real gases because the size is bigger. Particles, so easily they can reach each other. Small tiny particles means more time they take to reach each other. Bigger particles are there means quickly they reach each other. So time is less comparatively. Next is collision between the particles is perfectly elastic collision, but not in the case of real gases. Elastic collision means what? There is no force of attraction should not be there. But the stick means attraction will be possibilities that they stick and they may not be able to separate very quickly. That case is not a perfect elastic collision with the real gases. Next is kinetic energy depends only on the temperature. The kinetic energy of the ideal gas depends only on the temperature. More temperature, more kinetic energy. But in the case of the real gases, real gas also kinetic energy depends on the temperatures. But if you consider the total energy for the ideal gas is only purely kinetic energy. Whereas the real gases, total energy is the sum of the kinetic energy and potential energy. In the case of the real gases, total energy is the sum of kinetic energy and potential energies. because attraction also there between the molecules for the real gases. Next is ideal gas equation. Ideal gas equation gives the relation between the pressure, volume and temperature in terms of the number of particles, are called as in terms of number of particles or moles we take. That relation is pressure into volume equal to is proportional to absolute temperature. For this case PV is proportional to absolute temperature, proportional to if you remove that we will get as equals to mu into R. Mu is number of moles, we call this, sometimes we write as a small n also, nRT. We can write R is called as a universal gas constant. Capital R is universal gas constant, and capital T is absolute temperature in Kelvin scale. This mu is called as the number of moles. R is a gas constant, so proportional to if you remove, you can take PV equal to mu R into T. This also can be written as PV equal to small m into small r into T. This is not a universal gas constant. Small r is called as a specific gas constant. For the particular gas only we have to consider, and mu r, capital R is nothing but for the universal gas constant means universally for all gases that constant is applicable. And mu r into capital R is equals to m into small r. Small m is nothing but in terms of the mass we take. Mass, this is a specific gas constant, universal gas constant, and number of moles. This one you learned already in the thermodynamics, I think. Some equations will take from the thermodynamics in this topic also. Not some, many equations will come from there. Many terms also come from that. Next is in the real gases. One more thing is this gas equation, ideal gas equation can be written in terms of the number of moles. Number of moles is nothing but equal to mass by molar mass, means molecular weight. Mass in grams or kgs by molecular weight or atomic weight is nothing but equal to number of moles. This is also equal to number of particles by Avogadro's number. Avogadro's number indicates how many particles can be there in 1 mole of the substance. Mole is a number, just like the dozen. We can have dozen means dozen apples also 12 only, dozen bananas also 12 only. Whatever the items or objects you are taking, dozen means 1. 12. Dozen means 12, and here mole means the same number, that 1 mole of substance is always equal to Avogadro's number, 6.023 10 to the power 23 particles for 1 mole of substance. So from this formula you can calculate how many gas particles are present in. Next is so PV equal to, we can take it as equals to mu RT, can also be taken as NKT. This N into KT, N is the number of particles we take, number of gas molecules or atoms. KB is called the Boltzmann constant, it is MANN, BOLTZ, MANN, name of the scientist, Boltzmann constant it's called. And we, in this thermodynamics and gas problems, we take the temperature in Kelvin scale. Capital T is the Kelvin scale temperatures, small t in the centigrade scale we take. Advantage of taking the Kelvin scale temperature is it don't have the negative values. Kelvin scale don't have negative values, it starts from 0 Kelvin only, whereas centigrade and Fahrenheit scales can have negative values. So this PV equal to NKT can be written PV equal to mu RT. This is in terms of the number of moles, this is the number of particles or molecules. And this is for ideal gas equation. For real gases, attraction is there due to the reason the volume of the gas decreases by force of attraction to the molecules. The reason is due to the result, but some pressure increases here, and volume decreases. That real gas equation given by the scientist called as Van der Waal. This Van der Waal's real gas equation is P plus A into N by V square into V minus N into B equal to nRT. Here N, mu is a number of moles can be taken as mu symbol or the N symbol, but in these derivations of the Gadget theory we are going to take a number of particles per unit volume, that is number density is taken as a small n, so that you don't get confused with the symbols. Same symbols may be repeated for the different physical quantities. Here P plus An by V square into V minus B equal to nRT is a real gas equation called as Van der Waals gas equation. N is number of moles, A is a constant of the, but A and B are constant of the gases. It is called as a constants of the particular gas. They are different for different gases, and this part is not in your syllabus, you can neglect it. It is required only for the JEE examinations, not for other exams. Even NEET also they don't ask, but in this equation you can be given, this equation can be given even for KSET also, CET also, with this N equal to 1 mole if you are taken for dimensional calculation combinations etc. will take. This whole thing is pressure can be added to pressure. So this AN by V square has the dimensions of pressure. Volume can be added or subtracted from volume only. So N into B is supposed to be volume, N is just a number. So B has the dimensions of volume, units of volume, and A by V square, N is a number here, so A by V square has the dimensions of pressure. units of pressure we can take. Right side is nRT, and PV, this part is nothing but energy, pressure into volume as the dimensions of energy. So nRT has mu RT or NKT as a units dimensions of energy. So mu RT is energy related, PV also energy related, same in the case of NKT. Next, when does real gas, these real gases, in the daily life we have the real gas only, but we want to calculate the temperature, pressure exerted, etc. Theoretically if you take them as ideal gas only we have to take, but real gases when they behave as ideal gases, when they give is the condition is this important one. Real gas behave as ideal gas at high temperatures and low pressures. Low pressures, if you take the gas particles, large number of particles if you have taken, more number of particles or more number of moles, more moles means more particles also, then they collide more frequently with the walls. Due to that reason, whenever they collide they exert the force on the walls. Force by area of the wall is nothing but equal to pressure. So they exert the pressure on the walls which is holding these gases. So this pressure depends on number of particles or mass or moles we can take. If the number of particles are less taken, very few particles you have taken, then the pressure is also less. So at low pressures means few gas particles you have taken, then and increase the temperature. When the temperature is high, what happens is that kinetic energy of the gas particles increases. Temperature, kinetic energy depends only on the temperatures. More temperature, more kinetic energy. Due to that reason, the particles run very quickly away from all directions randomly. The force of attraction is present for the real gas also negligible when the kinetic energy is very large. Total energy is the sum of kinetic energy and potential energy, but kinetic energy is so high that potential energy is almost zero. That is possible at very high temperatures, and very few particles are taken. When few particles are taken, means the distance between the particles is very large. The interaction means force by attraction will be negligible. So low pressures, high temperatures, real gas behave as ideal gases. So gas equations what you are taking, the Boyle's law, Charles law 1, Charles law 2, or Boyle's law and Charles law. Charles law 2 is also called as the Gay-Lussac's law, named after the scientists. And Boyle's law states that P is inversely proportional to V, or PV equal to constant. What is the condition we take here is constant pressure and volume. All the three variables, how many variables are there in the gas equation is called as state variables, indicate the state of the gas. Pressure, volume, number of moles and T. R is a constant, we don't take it. Variable we can take is pressure, volume, temperature and number of particles. So here PV equal to constant we mentioned means right side part must be constant, that means temperature constant. That means Boyle's law is applicable at T constant. This case is temperature is constant, and also number of particles should be constant, number of moles should be constant. You cannot apply Boyle's law if the number of particles are changing. For example, if you take the balloon, you blow the air into the balloon, number of particles changes, volume changes, pressure also changes, pressure increases, volume increases, number of particles also increases. So that Boyle's law is not applicable here. In this case, if pressure increases, volume decreases and vice versa. For the given particles, number of particles n constant and temperature constant, then Boyle's law is applicable. Next, Charles law. Charles law states that is volume is proportional to temperature. So V is proportional to T. In this also number of particles should be constant and pressure is also constant. V is proportional to T means remaining all you have to take constant at a given pressure. So V is directly proportional to P means P is constant and number of particles is constant in all these gases. Equations we are taking constant supposed to be. If the temperature increases, volume also increases means gas try to expand. The expansion, why it is happens, any metal if you are heating it expands because of the vibration of the particles. For the solids if you take it heat expanded means the atoms or molecules are vibrate, due to that reason they expend more time outside also, that is the reason that metal appear to be expanded. So kinetic energy. Yes, for solids we talk about the vibration kinetic energy, liquid also vibration kinetic energy, here translated kinetic energy. That traveling in multiple directions exert more force on the surrounding walls. So as you heat the containers, the gas exert more force on the sides. The result is expansion. The reason is increase in temperature increases the kinetic energy of the gas particles. Next is the pressure also increases, that increase of temperature. But if a P proportional T means what you have to keep P constant is volume is constant here and number of moles is also constant. If the pressure constant called as isobaric, temperature constant is called as a isothermal. Here temperature constant is isothermal, pressure constant is called as isobaric, volume constant is called as a isochoric processes. And pressure is proportional to mu. More particles you have taken means more will be the pressure. P proportional to mu, or you can take a mass or number of particles. Next, the graphs. Graphs in terms of these equations, graphs if you check up, Boyle's law. Boyle's law graph is P is inversely proportional to P. Whenever the inverse related is, that means the graph should be a rectangular hyperbola. We can take P, V here or P here, V here, doesn't matter, exchangeable. P inversely proportional to means the graph between these two is rectangular hyperbola. This is for ideal gases. But real gases, the graph will not be exactly rectangular hyperbola because the molecules try to go close to each other. The result is the graph is a little curved like this. But if you increase the temperature, that becomes more ideal curve. This is the temperature, they will give you the problems. Generally for competitive exams, we have to identify the temperature ratios or relations. This is a high temperature. At high temperature, the gas behaves as ideal gases, so it becomes a more rectangular hyperbola, otherwise it's slightly curved ones. So T1 is greater than T2, greater than T3 is the temperature relationship. Next is, if you take the VT graphs, volume versus temperature graph, absolute temperature I am telling here. If you take the volume versus temperature graph, as the temperature increases, volume also increases because volume is proportional to absolute temperature at the given pressures and given quantity of the gas. So proportional, directly proportionality equation, inversely proportional. Directly proportional means should be straight, the graph should be straight line passing through origin. This is for ideal gas. But real gases, what happens? Real gas, if a temperature decreases, this is 0 kelvins. The Kelvin scale don't have negative values, it starts from 0 Kelvin only. So this is the temperature you are taking in terms of Kelvin scale. At 0 kelvins, the gas molecule volume goes on decreasing. Temperature increases means kinetic energy increases. Temperature decreases means kinetic energy decreases. That means they don't move at all. They are constant. That means volume becomes equal to 0. When temperature reaches to 0 kelvins, volume is 0. When volume is 0, we should not call it as a gas anymore. Or then may be converted into liquids or solids. Because gases means particles should be moving in the random directions, but they are not moving at all. Stationary means that behaves like a solids or liquids we can take. Similarly, if you take the pressure gas, pressure, in same condition you can take pressure here. Pressure versus temperature if you have taken, pressure will be there means gas particles are moving and colliding with the walls, exert the pressures because of the force acting on the walls. But if the temperature decreases, the kinetic energy decreases, they won't collide much with anything and just fall at the base because the gravity is there means they fall, otherwise they stand where they are. Kinetic energy 0 means they are not at all moving. 0 temperature 0 means 0 Kelvin, kinetic energy also 0, then pressure also becomes 0, pressure also 0. If the temperature reaches to 0 kelvins, the pressure and volume becomes equal to 0 means the gas will not be there anymore and gas converted into solid or liquids. Gas is converted to the solid into or liquid. This is in Kelvin scale. Same graph can be asked in the different ways. Centigrade scale, if they give pressure or volumes, they become 0 here. The temperature is minus 273.15 degrees centigrade. Negative values. Centigrade scale, if you have taken small t, 0 degree centigrade, the present volume will be there. But this is a case of the ideal gases. Straight line graph you have taken means that is for ideal cases. Real gas, what happens? Hydrogen, helium, etc. if you have taken, and of course inert gases, helium, that 7th group gases, helium, neon, argon, these gases are called inert gases. The attraction is very, very less, but still it is not 0. So they can be also liquefied. If there is no force of attraction to the molecules, we cannot liquefy the gases. Force is there means they can liquefy. Real gases can be liquefied. Ideal gases only graphically we mentioned, but not really can be liquefied. And we cannot reach the absolute 0 because to cool the materials, any cooling purposes, we take the help of the gases only. Even in AC rooms, refrigerators, we take the help of the gases expansion and absorbing the heat. But at absolute 0, if you are reaching close to absolute 0, there is no gas. Gas will not be there anymore. Real gas all will be converted the liquid into solids. Due to the reason we cannot reach to absolute 0 only. So far we don't have the procedure to reach the absolute 0, that is 0 kelvins. So what happens is before reaching 0 Kelvin only, the real gases, they are converted into pressure and volume becomes equal to 0. So different gases will reach to this 0 volume, 0 pressure. And this is one gas, this is another gas we can take. Less attraction is there between them, we will take a more low decrease in temperatures. So graph will be deviated towards the temperature axis at the high temperatures. for the graph between the pressure and temperatures. But at high temperatures, what happens? Temperatures high means they have the similar properties. They behave like ideal gas we discussed already. At high temperature, they behave like ideal gases. Otherwise, they deviate towards the temperature graph. But in your textbook, they mentioned in the taking the temperature on the y-axis, pressure and on the x-axis they mentioned, or volume they mentioned in the graph. If you take the temperature and pressures, volumes, at high temperature they are similar graphs. You will find straight lines for different gases they have taken, as a different pressures they have mentioned, means different amount of the gases. So as the temperature is decreased, they bend towards the temperature axis, because they will be liquefied. Pressure becomes equal to 0. They are supposed to be passing through the origin, supposed to, if they are ideal gases. The pressure relation they will give you P1, P2, P3s. Here I took this graph in reverse, volume, pressure, temperature. Towards the temperature graph they will bend, and this relationship for the pressures P1 greater than, P2 greater than, P3. How do you know which one is more in this graph? Since in the examination, also competitive exam, they will ask you the different graphs. If they give the different graphs like this say P1, P2, T and V, they take the reverse cases here. We have the relationship V proportional to T relationship, or PV equal to, we want to get the P relationship. So PV equal to N or T relationship we have. One T or V you keep constant for a given volume we take. V constant I am putting. Then P is proportional to temperatures. More temperature, more pressure. So if you take the intersecting here, this graph you check it out. P2. This is a P2. This intersecting is here. This is going to be corresponding to T1, this is T1, P1 is T1, P2 means this is going to be P2, which is more in this direction. Temperature is increasing, so T1 is greater than T2, T1 is greater than means P1 is greater than P2. So to get to which one is more, we have to take the intersecting, keep one of them constant here, either T constant or V constant, and get the expression. V constant means T, more pressure. V constant means more P, more temperature. So we can say that P1 greater than, P2 greater than P3. Even if they change the graphs axis also, you must be able to calculate that. These graphs are important for competitive exams. Next, the first graph mentioned here, PV equal to mu RT, or PV by mu RT is supposed to be equal to 1. Mu is number of moles. It is equals to 1 only for the ideal gas. But the real gas if you take means that is not equal to 1 always. When as the temperature increases, that the real gases becomes close to ideal gases. So the temperature ratio they will ask which temperature is more means in this case T1 is greater than T2. And this is supposed to be ideal ones. As the temperature increases, the graph property shifts close to the ideal cases. T1, say this is a T1, T2, T3. T1 is more than T2, greater than T3. Next, this derivation, the expression for pressure of the gas in terms of kinetic energy. Gases, liquids, solids. What is the difference is, if you take the solids like ice you have taken in the cubical form, molecules of this solid are very close to each other throughout. If you melt the ice, what happens is, this is disintegrate. If you melt the ice, that is converted into water. And the water compared to this ice, what is the difference is, the distance between the particles is more than that of the solids. Solids have the close compact of the particles and the molecular vibration is less here. But here, vibration of the particles is free to move and free to vibrate also. These are liquids. This is a solid state. Next, if you supply the heat further to this water, it becomes equal to steam and converted into gaseous state. What is happening in the gaseous state compared to the liquids? Is the gas particles have the distance is more from each other. Why? Because the kinetic energy is very high here. As you are heating this, the heat energy converted into kinetic energy of the particles, as a vibration of particles, and try to get away from each other. So converted into liquids, the distance more, and converted into gases, the distance is still more. In this liquid converted into gases, still more. So what is the whatever supply it is or supplying is stored as energy inside the material, that is called as internal energy. Internal energy is very less for solids, but high in the case of the liquids, still high in the case of the gases. Gases have the very large kinetic energy because of the internal energy is very large, and we are talking about only ideal gases, therefore we have only kinetic energy. Now potential energy we discuss. Potential energy there means they can be attracted towards each other. It is possible to convert into liquids or solids. So if you are cooling the gases, what happens is the distance between the particles decreases because the kinetic energy decreases, and less heat is in the less internal energy, less heat energy inside the solids compared to liquids compared to that of gases. Gases have more internal energy. Due to that reason, they have always tried to go away from each other. And compared after gas, what you have is the plasma state that we are not going to discuss now here. That is the fourth state of matter, possible only at a very high temperatures. Next, expression for pressure of the gas. We take the ideal gas in a cubical container, small container of side equal to L. So surface area becomes equal to L into L, L square, length into breadth L square, volume becomes equal to L cube. In this, there are two methods of the calculation of the getting the result. One is particle traveling only one direction we can take, but in this derivation of what I am doing is particle collided with a wall and went to the other wall and coming back, colliding with the same wall. After collision, first collision, second collision, time interval is nothing but equal to delta t or t we can take. In this time interval, the distance traveled is L and L. Other method is particle traveling only in one direction we have to take, only L distance traveled. Here I am taking is going forward and coming back just after collision, again when it collides next time. That interval, time interval we are taking as a delta t, with the same wall, consecutive collisions time interval we are taking, then the distance traveled is L forward, again L forward, backward, total distance is 2L. One direction velocity we can take as a vector form, we can take in reverse means coming back speed we can use. Magnitude of the velocity itself is speed. Next, consider monatomic gas, ideal gas, inside the cubical box of side L. Surface area is L square, volume is L cube, mass of the particles is m, and we use the term called as n, small n, number of, not number of moles please. N is equals to this total number of particles by volume is called as a volume density of the gases. That end we will discuss. Small m is the mass of the each particles. Capital M we take is equals to mass of all the particles, and m naught we take for the molar mass. Okay, that we will discuss later. Here we take a volume. Volume is equal to L cube, and capital N is the total number of gas particles, and mu is the number of moles. Number of moles is mass by molar mass. Next, particle traveling, consider the particle, one particle traveling, particles travel along XYZ axis. We are considering the monatomic gases here for in the beginning, later we discuss about the diatomic, polyatomic gases. So these gases can travel in multiple directions. We take X axis, Y axis, Z axis, so in all directions we are taking, but when you are taking a large quantity of the gases in the room, they travel randomly such that the number of particles going one side equal to number of particles going opposite directions. Otherwise what happens, if the fan is there, that pushes the air molecules in one direction, that means one direction is more than the other, but there is no wind, there is no pressure difference. Constant pressure in the room you maintained, or constant temperature, constant pressure you are maintaining means the particles travel randomly such that number of particles going in one direction equal to number of particles going in other directions, means approximately equal number of particles going in X axis, Y axis, Z axis, the assumption we take. Next, T is the time interval with the two collisions of the gas particle with the same wall. We are taking the same wall, going and coming back and hitting the same wall after time interval equal to T or delta T we can take. We are taking the particle traveling in the X axis. Then speed along the X axis is nothing but equal to speed equal to distance by time. The distance traveled is 2L and time taken is T. And during if you take the velocity terms, value of the velocity is nothing, magnitude we are taking here, but if you take the wall, on this wall, if you take the elastic ball hitting this with velocity v and mass is m, so mass into velocity is the momentum. Afterwards it bounces backwards. Considering the elastic collision, we are considering the elastic collision here. When the elastic collision is there, means there is no loss of kinetic energy. Then a particle comes back with the same speed equal to v, then momentum is mv. Forward direction is plus momentum, backward direction is minus momentum because momentum is a vector. So change in momentum becomes equal to final minus initial. Final is minus mv, initial is mv. So final minus initial means minus mv. Minus means minus of 2 mv is nothing but a change in momentum we are taking to. Any object returning backwards with the same speed, then change in momentum is 2 mv we have to take. W you have to take, don't take 0. Then this is a momentum change of the wall. So that while hitting the wall, it exchanges the momentum with the wall. that exert the force on the wall, and the momentum for the wall transfer to the wall is nothing but equal to, if this is a minus, means for this is going to be plus, because change in momentum by time is nothing but equal to force. Force is nothing but change in momentum by time. Action is acting on the wall, then reaction is acting on the ball to bounce backwards. So here in place of the ball we are imagining the air particles. So change in momentum is nothing but equal to 2m into Vx along the x-axis. Force on the wall is nothing but equal to delta. Force exerted on the wall is nothing but equal to delta px by t. T is nothing but equal to 2l by T is equal to 2l by v. 2l by v. V go to the numerator, becomes equal to Vx square. So force is nothing but equal to change in momentum by time, becomes equal to 2 cancels here. So m Vx into Vx is Vx square by L, it becomes is the force. Next is in 3 dimensions if you consider, that means force acting on the all sides if you are taken according to Pascal's law, force is uniform in all directions. So but a force, if you are taking the resultant of all the particles in the gas in the container, particles are traveling in different directions. So but approximately we take the velocity same along the x-axis, y-axis, z-axis when the large quantity of particles are taken, Vx equal to Vy equal to Vz. Then this velocity what you have taken, Vx square, we take the average speed, average velocity of the particles in all directions together, we take it as the mean velocities. Just like the vector additions, if you take no Vx square plus Vy square, Vxi plus Vyj plus Vzk terms like that we take, and magnitude square, velocity equal to Vxi plus Vyj plus Vz square. Magnitude, these are the under root Vyj plus Vzk. If we take the magnitude, no, V square is equals to V1 square plus V2 square plus V square, means Vx square plus Vy square plus Vz square is a magnitude. We are taking the magnitude term here, similar case. So V square is equals to Vx square plus Vy square plus Vz square. But Vx, Vz are nearly equivalent, putting the values here, this is also Vx square, Vx square is 3 Vx square you will get. So Vx square equal to V mean, means average speed by 3 square only. These are mean square values, mean square of the velocities. Vx square equal to V mean square by 3. V mean square, substitute the value term there. So what you get is, for this all particles are taken here, 3 dimensions, all particles. All particles means you need to consider the total number of particles n now. Then total mass, each particle mass is small m, total mass becomes equal to n into m. So this n into m is nothing but equal to total mass of gas, it becomes. So if you substitute here, for total mass you are taking here, total mass exerting the force is nothing but equal to F is nothing but equal to, wherever small m is there, now replace with the Nm into V square, Nm into V square by L. But Vx square is replaced with V mean square by 3, so 3 comes here extra. Nm into, from this relationship, and Nm is equals to, total mass is equals to Nm, total mass. This substitution you are getting this relationship, but the total force it is. Total force acting on the wall, any wall we can take is this much. So pressure is nothing but equal to force by area. Pressure equal to force by area. Area is nothing but equal to L square. Any surface area you take equal to L square. So already L is there. So L into L equal to L square. L square into L becomes equal to 3L, L cube. This is a force by L square, means L cube, and 3 remains as it is, Nm into V mean square. Here is L square. The pressure becomes equal to this term, Nm by 3V. Volume, L cube is nothing but equal to volume into V mean square. This is for the total gas. V equal to L cube volume. Next, total kinetic energy of the gases. Kinetic energy of the gases, for each particle gas is nothing but equal to half m into V mean square. This is nothing but a microscopic formula of the kinetic energy of the particles, each particles. But total kinetic energy of gas particles if you are taken is nothing but equal to number of particles into kinetic energy of each particle becomes equal to total kinetic energy. So this term can be written as Nm into V mean square by 2. By 2 into 2 cancels. So the result is this one becomes equal to kinetic energy, we can write. Modifying the equation to get the expression for kinetic energy is nothing but equal to half into total mass into V mean square is kinetic energy into V by 2 by 3. 2 extra terms comes in the final expressions. So what happens is P equal to 2 by 3 into this kinetic energy by V, and V can take it to the left side, becomes equal to PV. PV equal to 2 by 3 into kinetic energy. Present volume as the dimensions of energy. This is a kinetic energy symbol may be given as only E can be given, or symbol can be given as K also. I gave it as K dot E for kinetic energy. In some expressions, the textbook expression they mentioned this N. In place of N, by V. N by V replaced with small n, and called as the number of molecules per unit volume. Volume 1 unit means 1 cubic meter or 1 centimeter cube. We have taken N by V is equals to small n. So this formula he modified this as equals to small nm into V mean square by 2. 2 can cancel, of course. This is the expression derivation for the pressures. Next day one more derivation is there. One or two derivations are there that we will discuss in the next class.